We can now consider the underlying principles of Le Chatelier's principle. At AS level, we took it for its word, so let's try and explain it in terms of equilibrium constants. So first of all, let's look at what happens when we change the concentrations of a reactant or product at when its reactions at equilibrium. So we have a reaction of sulfur dioxide and oxygen here, producing sulfur trioxide. You could use Kc or Kp for this, doesn't matter. Um, uh, so the result will be the same. We use Kp because that makes sense. So Kp is a fixed number, it's a fixed constant at a fixed temperature. It will only vary if the temperature changes. So Kp must stay the same. So whatever I do to the concentrations, how many moles of SO2, O2 and SO3 I mix at the beginning, it will reach equilibrium so that those partial pressures result in Kp being that number, always that number at that temperature. So, for example, let's say I had Kp and I'd worked out the partial pressures of SO3, SO2, and O2, and I pop those in the equation now, and you can see that SO3 is squared and SO2 is squared. If I do that, it becomes 25 over 36, which is 0.695 atmospheres to the -1. So this is just an example of what Kp could be at a certain temperature. So that's the full working out there, just to remind us. So now let's say I'm going to add in some SO2. So it's reached equilibrium. Kp's at 0.695. Everybody's happy, and I come along and I add in some SO2. And it increases the partial pressure of SO2 to 6 atmospheres. So that would change initially because SO3 would be the same, O2 would be the same, but SO2 has changed dramatically, which would mean that Kp would change, but it can't change. It must remain that number. If we work that out, that would be 0.1736. So we need to sort something out because Kp has to be 6.95 atmospheres to the -1. But because I've added all this extra SO2, the partial pressures are now giving me a Kp of 0.1736. So obviously that has to increase from 0.1736 back up to 0.695. And in order to do that, the partial pressures of SO2 and O2 need to decrease and the partial pressure of SO3 increase. Therefore, as Le Chatelier predicts, the equilibrium would move to the right. So we can have a look at this in a little bit more detail. So again, there's my original Kp, and I now need to find a new Kp, need to change those partial pressures so that I can get back up to 0.695. So, I say there's a reminder of my new conditions. They're not at equilibrium because I've increased my partial pressure of SO2 significantly, but the SO3 and O2 haven't changed. So I have to re-establish my equilibrium, and I could perhaps do that by the 6 for atmospheres for the partial pressure of SO2 becoming 4. And the partial pressure of O2 becoming 3, and that would mean that the partial pressure of SO3 becomes 5.78, and that would again give me a Kp value of 0.695 atmospheres to the -1. So we can now look in more detail at the effect of changing pressure on Kp and Kc? Well, of course, first of all, Kp and Kc have to stay the same value despite any change in pressure. So let's take our sulfur dioxide oxidation equilibrium again. And we'll say that we started with a total pressure of 4 atmosphere, which meant that when we came to work out Kp, it was the mole fraction of each of those molecules times by 4, which I've put there. So YSO3 is the mole fraction of sulfur trioxide, etc. So when we look at that, we can see that it's going to become the 16 multiplied by y squared. And then on the bottom part, we have 16 times y squared times 4 multiplied by y for oxygen. And so therefore, when we multiply all of that out, it becomes basically 16 over 64 with the relative mole fractions staying there. So that's with our total pressure of being 4 atmospheres. Let's say we're going to now increase our pressure to 6 atmospheres. So we're going to change those values from 4 to 6. And if we do that, of course, the system is no longer at equilibrium if the mole fractions remain the same. Because if we do that, we will have those mole fractions now times by 6, which when we work it all the way through, it becomes 36 over 216. And so comparing those two together at equilibrium, it's 0.25 times the mole fraction expression, but at 6 atmosphere, it becomes 0.167 times the mole fraction expression. So, and that, it can't be, it must remain to be 0.25, and therefore we need to start shifting some moles about. So, equilibrium, we had it to be 0.25, and our new conditions were 0.167. So we went from 16 over 64 to 36 over 216, which was an increase of 2.25. In the numerator, and in the denominator it was an increase of 3.375. So hopefully you can see that that change in pressure has affected the reactant more than the products. Remember, in Kp, the reactants are on the bottom of the fraction. And so in order to restore Kp and get back to our original equilibrium value of Kp, the mole fractions of our reactants have to decrease and the mole fractions of the product increase. And therefore, that means that our equilibrium will shift to the right, which of course is the side with the fewest gaseous moles, as predicted by Le Chatelier. Right, so changing temperature now. We'll stay with our sulfur dioxide equilibrium, and we've got delta H now as being minus 198.2, which of course means it's an exothermic forward reaction and an endothermic backward reaction. So when we pop that into Kp, like so, any increase in temperature we know will shift the equilibrium in the endothermic direction. So in this reaction, the number of moles and partial pressure of SO2 and O2 will increase, and therefore Kp will decrease. So remember, temperature is the only time that the value of Kp will change. So if we now decrease the temperature, that will shift the reaction in the exothermic direction, and therefore the number of moles and partial pressure of SO3 now increases, and Kp will therefore increase. So that was a explanation of how we can use the equilibrium constant to explain why Le Chatelier's principle works. If you're more interested in why the change in temperature does affect Kp and Kc, um, you can follow the link to the next video. But that is extension material. You don't need it for the A-level course. But if you're interested as to why that happens, if you follow the link, and we'll look into that.